Let's try this. All right, so let's move on. So we're talking about this kind of hypothesis where we have alpha is 1%, two-tailed test. And I think we had done this earlier on. We were checking here before we got disconnected. So the critical value we said is how much? I think somebody had seen it.
2.58.
2.58. Plus and minus. Minus 2.58, 2.58 on the plus. So once you do that, the next step is just to obtain Z calculated. I'm trying to combine step number 3 and 4, or 4 and 5. So Z calculated will be obtained using this formula, mu naught. What did I say up here? Yeah, that's okay. I think I want us to put a 0 here, not here, to avoid confusion, because mu will never be known. So here we're working with a mu naught. So please insert this naught here. X bar minus mu naught. X bar minus mu naught. Please go up there and check that beta. So here we're working with the X bar minus mu naught divided by the standard error of X bar. So let's obtain the standard error of X bar, which is, in this case, we don't have sigma, so we'll use S over root N. And our S is 1.6. Then our N is 100, so we are going to have it like that. So our standard error is 0.16. So we continue. Our Z calculated will be X bar, which is 20.5. X bar is 20.5 minus our mu naught. Here we're using mu naught, 23.2 divided by 0.16. So that is our Z calculated. So 20.5 minus gives you minus 16.875. That's what Z calculated. So the next thing is to say whether this value falls in the acceptance region or in the rejection region. So we are now at step number 6. So if you try to locate that value here, it will be somewhere here, not drawn to scale, minus 16.875. It is deep in the rejection region. So you say that first. You say that Z calc, which is minus 16.875, falls in the rejection region or the critical region. So once you observe that, it tells you what to do with the null hypothesis. You reject the null hypothesis. So hence, we reject the null hypothesis. If you want, you can mention the null hypothesis, which is H naught, that mu is equal to 23.2. If you want, you can mention that. We reject the null hypothesis at the 1% level of significance. The null hypothesis at the 1% level of significance. Level of significance. Level of significance. But that's not your conclusion. Actually, that was not our objective. We were just using mathematical approach or statistical approach to arrive at that point. We need to answer the question. There is a question that we are trying to answer here. There is a question that we are trying to answer here. So let's try to answer the question. So what is our conclusion? Or what's our decision? Let's go back. Let's revisit the question. It's always good that you check the question, because whatever you say there must be directly answering the question. So let's check here. This was the question. We need to test if the sample, this is what we are testing, if the sample or whether the sample comes from a population whose mean is that. So if you are to give me a one-word answer, yes or no, what would you say? From what we have done, the hypothesis that we have tested, do you think the sample that we are given here comes from a population whose mean is equal to 23.2? Yes or no?
No.
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 Okay. Because this is what we have done. We have rejected this. So once you have rejected that, it means that this is true according to the data that we have. So hence, so our conclusion is that the sample does not come from a population whose mean is 23.2 hours. So that's the answer to the question. You report in layman's language. You report in the normal language, not statistical language. The sample does not come from a population whose mean is 23.2 hours. Alternatively, you can also say that by saying this. Alternatively, the sample we can say that the true population mean, the true population mean I'm trying to avoid some duplication. The true population mean for the population from where the sample was drawn, is the true population mean. In other words, you talk about mu here. So the mu of the population from where we got this sample from is not 23.2. So this sample, in other words, this sample came from a population whose mean is not 23.2. So those two statements are equivalent. You can use whichever you feel is easier. So basically, that's how you test hypothesis. That's how you make your conclusions. I want us to go to part 2 of that question. Part 2 of that question. We are still given the same information, but now I think they are giving us a new alpha. If you are given alpha is 5%, you want to do a similar test at 5% level of significance, test whether this sample comes from a population whose mean is 20.8 hours. So in this case, we are changing alpha to 5%. You test whether sample comes from a population whose mean is 20.8 hours. Okay. So in this case, we are noting that we have a new value of mu naught. Our hypothetical mean value is 20.8 hours. 20.8 hours. So let's test our let's define our hypothesis. So solution H naught is that mu is equal to mu naught, and our mu naught is 20.8 hours or 20.8 hours. Yeah. Then H1 will depend on the question, how the question is asked, but must have a mu, must have this value here. Test whether it comes from a population whose mean is that. So just like the first one, here we're testing not equal to. So that question and the first one are equivalent. They are the same. The only difference is the values of mu naught. So once you know that, that is calling for a two-tailed test. at alpha is 5%. So that kind of hypothesis is calling for a two-tailed test like this. So this is alpha over 2, which is 2.5%. This is also alpha over 2, which is a 2.5% or 0.025. So we need to get our Z critical here, Z crit, and here also Z crit. Okay, so this will be 0.475. From your tables, this is the most famous critical value of Z. So Z crit is plus minus 1.96 from the table. Okay, so once you get the critical region, once you set up the critical region, the next thing is to obtain your Z calculated. It's always given by X bar minus mu naught standard error of X bar. So in this case, standard error of X bar, this value has not changed. It's similar to the one we saw above. The same sample. Eh? So no change there. Yes. So then X bar, we're given X bar is 20.5. And here we have 8, 0.16. So what is our Z calculated in this case? Minus minus 1.875. So once you get Z calculated, you check whether it is in the acceptance region or in the rejection region. In our case, this value will be here. So this is minus 1.96, huh? And this is 1.96. So this value is here. This value is here. Let me write it in red or some other color here, like black. Minus 1.875 is somewhere in the acceptance region. So that's the first thing you record. You say that Z cal is minus 1.875 is in the acceptance region. In the acceptance region. So that tells you what to do with the null hypothesis. We do what with the null hypothesis?
You accept.
We fail to accept.
We fail to reject.
We fail to reject the null hypothesis. We fail to reject. Hence, we fail to reject the null hypothesis at the given level of significance. We fail to reject the null hypothesis at the given level of significance. So what's our conclusion? We go back to the question that we are trying to answer, and we respond to that question specifically. So what do you conclude? The question is, does this sample come from a population whose mean is 20.8 hours? Yes or no?
Yes.
Yes.
So the sample comes, so we conclude that the sample comes from a population whose mean is 20.8 hours. Sometimes we say it's not different. It's not different from 20.8 hours. So basically that's the conclusion. That's how you conclude. So maybe you can have our third example there. I think now we're using alpha is 1% to test whether the sample comes from a population whose mean is less than what?
Volume it is 5%.
Oh, Where?
At 5% levels. Whether.
Oh, the last one. Thank you. So this is 5%. You have good eyes, huh? At 5%. We can even do it at 1%. Doesn't matter. Actually, I want you to do it at home at 1%, whose mean is less than 20.8 hours. All right. So let's repeat the steps or the story. So clearly, you know, this is our mu naught. So our solution H naught will be mu is equal to 20.8. And then we are testing whether it is less than. So you see the question is the one that will always guide you. So here we have H1, mu is less than 20.8. 20.8. So that is calling for a lower tail test. That calls for a lower tail test. So you put all your 5% here. So this will be alpha is 5%. And then here you have your Z critical. And then I can just write it here, Z crit. What is the value of Z critical? 5%. Let me bring these guys on board. Huh? Let me bring the tables on board. I hope there'll be space for them.
0.95.
Yeah. So what is this? What is this area here? 0.45. Huh?
Jesus.
We are working this value here. So in between there, and we said that we prefer to work with the value. In this case, it will be minus 1.65. Okay. So then after that, we obtain our Z calculated, which is given by X bar minus mu naught over standard error of X bar. And we know the answer, isn't it? We know the answer. Minus 1.875. Okay, so we now make a decision. This is a minus 1.65. So we make a decision. Where is this value? When you come here, clearly this value will be in the rejection region. It will be somewhere in the shaded part. So we say that Z calc, which is minus 1.875, falls in the rejection region. Okay. And that tells you what you're going to do with the null hypothesis. Hence, we reject the null hypothesis. We reject the null hypothesis at the given level of significance. At the given level of significance, we reject the null hypothesis. Now, what's the conclusion? Conclusion. Our conclusion, we have to answer the question. What is the question that we're answering here?
Chicken joy.
So what's the question we're answering here? We are trying to answer the question whether the sample comes from a population whose mean is less than 20.8. So is it a yes or no before we write?
No.
Is it a yes or no? Remember, our null hypothesis looks like this. H naught, mu is 20.8, and H1 mu is less than 20.8. We have done this, we have rejected this statement. Is it so?
No.
Did we reject the null hypothesis?
Yes.
Yes. We have rejected the null hypothesis. What did you do in this other question? Okay, yeah, that's okay. So we have rejected the null hypothesis. So is it a yes or no? Does the sample come from a population whose mean is less than 20.8?
No, no.
No.
Uh-huh.
Yes.
Yes.
So the sample
Comes.
from a population whose mean is less than 20.8 hours, according to the data that we have.
Oh, yeah.
The sample comes from a population whose mean is less than. This is how you look at it. We have rejected this statement. We have rejected this statement or this hypothesis. This is what we have done. We have done that. So once you do that, it means that you have done that also here. So according to the data that we have, this is the truth in quotes. The truth will never be known here. Okay. So the mean, the population mean is less than 20.8 hours, according to the data that we have. Hope that is home and dry. Hope that is home and dry. So let me see if I have another question here. I have this question. I want us to try this question. A sample of 150 students had an average IQ of 112 with a standard deviation of 9. We are not going to solve part B because part B is easy to see. We do that at home. So let's answer the first question because the first question is not obvious or it's less obvious. So we have a sample of 150 students whose average IQ is 112 with a standard deviation of 9. What do we have? What is 150?
N.
Small letter
N.
sample size. Then we have this guy here.
X bar.
X bar.
Bar, because it is coming from the sample. That's how you know. It's not guesswork. It's coming from the sample. Then finally, this one is also coming from the sample. So this will be S9. At what level of significance do you accept that this sample is taken from a student population whose average IQ is 110? So what is this 110? What is 110?
Mu not.
The hypothetical population mean. Correct. The hypothetical population mean 110. So the question here is alpha. Okay. So this question is different from the ones we have solved. So we're looking for alpha. At what alpha are we going to accept the null hypothesis that corresponds? You see, we are accepting the null hypothesis. At what level of significance are we going to accept, in quotes, the null hypothesis that corresponds to that question? So let's go back here. Example 2. We are given n is 150, x bar is 112, s is 9, and we are given mu naught is 110. The question is, at what alpha, at what level of significance do we accept, this word accept here should be in quotes, the hypothesis that mu naught is 110. I have paraphrased, so you'll get the real question from the notes. So the starting point always is to define your hypothesis, the null hypothesis and the alternative hypothesis. That's the starting point. H naught will be, H naught is easy to see for everyone. Everyone can see H naught. No, sorry, yeah, that's correct. Mu is equal to mu naught. Then H1 must have a mu, will also have a 110. But what are we testing? What is the question all about? Is there anything to suggest a greater than sign or a less than sign, or we're just testing for difference from this story here? What do you think?
Difference.
Not equal.
It's nothing.
Yes?
Not equal, not equal.
Not equal.
So this
Not
test here is calling for a two-tail test, not equal to. So either the population mean is 110 or not 110. That's basically it. So this is calling for a two-tail test. So on one side here, we shall have alpha over 2. Very important for you to note. And on the upper side, we have alpha over 2. Remember, alpha is not known. Alpha is the guy we are looking for. Okay. So we just go to the next step. Don't get stuck there. Let's go to the next step. Z-calc will be X bar minus mu naught over standard error mean. So where standard error of mean will be S over root n. Now S is 9 divided by root 150.
Zero point seven three four
0.734.
0.734.
748, etc. Okay. Now, so let's get our Z calc. So this is 112 minus 110 divided by that value. This is 2 divided by that answer. Which gives us 2.72. For Z, yeah, you are getting 2.8. For Z, I just need 2 decimal places because the tables that we're using are rounded off to 2 decimal places. So I'll just round it off to that value. So now this is what I want to do. I want a level of significance that will make this guy 2.72 fall in the acceptance region. I want to accept this in quotes. I want to accept this null hypothesis. So I want a level of significance that will make me fail to reject this. So the most convenient point where I can put this value is not at the center, is at the border point here. So that's where the acceptance region begins. That line marks where the acceptance region begins. So all this is the acceptance region. And of course, remember, you want to make alpha as small as possible. You don't want to put 2.72 or your acceptance, your Z calculated, you don't want to put it in the middle somewhere. So you put it at the border point there. So set this value minus 2.72 and this one 2.72. So that value is the one that will give you a level of significance that will help you to fail to reject the null hypothesis. So now you go to your tables and check the area corresponding to that value of Z. So I think our tables are still here. Yeah, they did not get lost. So our tables are here. Our Z is 2.72.
0.49.
This is the guy. 0.4967.
0.967.
So which area is that? Which probability is that? That corresponds to which area? Yeah?
0.5.
So where do I write 0.4976? Where do I write that value?
On the right side.
The acceptance part.
From where to where? That is
From mean to 2.75.
from the center, 0.4. It is 4.4 what? 9?
4967.
67.
4967. So that is the area from here up to that point. From the mean or from the center to 2.72. So from there, are you able to find alpha? Please work out alpha and confirm that alpha is do a few calculations there. Confirm that alpha is 0.66%. Any successes?
Yes.
Oh.
Yes.
0.66, huh?
Yes. Yes.
Very good. If you're getting that, it means that you are attentive to what is happening there. There are people who are stuck at 0.33%, isn't it? Yeah.
Like
Try to get unstuck.
0.33 is half alpha.
Whatever you have is alpha over 2. Whatever you have is this guy here, alpha over 2. So if you need alpha, you multiply both sides by 2. So please check there's a poll which is going on. Huh? There's a poll which is going on. So as you do your stories, keep checking. Huh? I want to know how the attendance looks like, especially across the campuses. So far, 75% are from town campus. There's 14% from main campus. There's 5% from Tengela campus. And the remaining 5% from Western campus. There's no one from distance learning here, which is okay. Okay, then everyone here is a BCom. 85% are finance students. 8% are accounting students. HRM. I wonder what is happening with marketing students. Where are they? Where are marketing students and entrepreneurship? Or they are not here. They need to join this class. Or maybe they're in class B, it's possible. I guess we are okay with that question. So the remaining part, part B, I know you can solve part B at home. Part B of this question, at the 5% level of significance, would you accept that the student population had an average IQ greater than 113? I'm sure you can test that because now we have a mu naught, which is 113. So that means your hypothesis will look like this. H naught mu is 113. You test that against mu is bigger than 113. So your critical region will be entirely on the upper side. It will be 0, this will be 1.65. Okay. And you get your Z calc, which will be X bar minus mu naught over the standard error. of X bar. Standard error has not changed, so you'll use the same value we got in the previous question. I'm sure you can do that. Now, I want us to move on. Let's move on. I'll give you some practice questions. I want us to move on to hypothesis testing when we have two sample means. Hypothesis testing for two sample means. Okay, so hypothesis testing. When you have two samples, and here basically what happens here, the story changes a bit, but not significantly. So here we test whether the two sample means are equal. So here we test for, let me paraphrase, here we test whether the two sample means are coming from the same population. We test whether the two sample means are coming from the same population. That is, if they are equal, and the converse is if they are different. They are equal or different. So the theory is, if we have two samples here, sample one and sample 2. If you obtain X bar from this sample, let's call it X bar 1, then you obtain X bar from this sample, there's a possibility that these two samples are coming from the same population. Maybe the population is somewhere here. There's a possibility that these guys are coming from the same population. If that is so, then we claim that X bar 1 and X bar 2 are not significantly different. So we claim that X bar 1 is equal to X bar 2. Or you can say that X bar 1 minus X bar 2 is equal to 0. And this is basically what we are trying to test, whether X bar 1 minus X bar 2 is equal to 0. But the hypothesis, as you know, we don't use X bar in the hypothesis definition. So we assume that they are coming from different populations. So the assumption here will be, we have a population 1 and we have another population 2. And from here we get X bar 1 and here we get X bar 2. If the populations are actually different, then here we have mu1, mean of the first population and mean of the second population. If the populations are actually different, then mu1 will not be equal to mu2. But if the population is just the same, in other words, if the samples are coming from the same population, then mu1 will be equal to mu2. So that will be the story. So our hypothesis now will be defined using these parameters here, mu1 and mu2. So this is how we define the null hypothesis in this context. So let's say that this story is here. So this is how we define the null hypothesis. So H naught is always defined as mu1 is equal to mu2. In other words, the two samples are coming from the same population. When mu1 is equal to mu2, it means that the population is the same. And the alternative has 3 possibilities. There are 3 possibilities for the alternative hypothesis. That is, either mu1 is bigger than mu2, or H1 that mu1 is less than mu2, or H1 that mu1 is different from mu2. And in this context here, we do not have any hypothetical population values. We do not have any hypothetical parameters. The hypotheses are defined in form of mu1 and mu2. The hypotheses are defined in that format. We don't put any specific values here. So clearly this is calling for a one-tail test, which is an upper tail test like this. Just like we discussed earlier on, this one will be calling for a lower tail test. I'll not go to the details because we have already mentioned them. This one is calling for a two-tail test like that. Okay. So the other steps are the same, but now we also change how we compute our Z. Z calculated, we use the formula x bar 1 minus x bar 2 divided by standard error. X bar 1 minus x bar 2. So this is called the standard error of, or for the difference of means. Standard error for the difference of means. Standard error for the difference of means. And it's defined as follows. So define it as follows. So this is equal to square root sigma 1 squared over n1 plus sigma 2 squared over n2. When the sigmas are not known, use s. So you have s1 squared over n1, s2 squared over n2. Where s1 is the standard deviation of the first sample and s2 is the standard deviation of the second sample. n1 is the size of the first sample, n2 is the size of the second sample. That is basically it. The other steps are the same. How you reject the null hypothesis and so on and so forth, you follow the steps that we discussed earlier on. Example. So let's pick the example from our notes. So let's pick the example from our notes. So we have this story here. We have this story here. Two factories producing some computer units. There are two factories which produce some computer units. And we are told to use the following sample data to test whether the two production lines are producing units with the same mean life of length. To test whether the two production lines are producing units with the same mean life of length. So let me summarize that story here. That information can be summarized here. So this is a table we are given there. We have number one. So given there. We're given x bar s and n. We're given x bar s and n. So the mean of the first sample we are told is 20.5. This is 19.0. Standard deviation of the first sample is 3.4. 1. Then we have 125 and this is 125. 180, yeah. This is 125. That's the information we have. There's a chart.
125 and 180.
Yeah, Paul Barre, you seem to be having some challenges, or you are just enjoying yourself with Assumpta.
Things are getting tough, but I'm following slowly.
Yeah, things will always be tough, my friend.
Sample 2.
Yeah.
N is 180.
Oh, 180, yeah. Yeah, thanks. You should get tough as the things get tougher. So from this story here, x bar 1 is 20.5, just to bring everything to perspective. S1 is 3.4 and N1 is 125. Then X bar 2 is 19.0, S2 is 2.1, and N2 is 180. So that's what we have. So which hypothesis are we testing? H naught. H naught will be the same for all these kinds of hypotheses. H naught will be the same for all the hypotheses. Huh? So please, if you want to say something, if you're looking for my attention, just talk, because I rarely check the charts. Huh? I rarely check the chat. So if you want to say something to me, just interrupt. But if you are just enjoying yourself, you can post in the chat. Okay. Then H1, this will be guided by the question. But of course, we shall have a mu1, we shall have a mu2. So what is the question that we are trying to answer here? Test whether the two production lines are manufacturing units with the same mean life of length. So what are we testing there? Is there something to suggest a greater than, a less than, or we are checking whether they are different?
Not equal to. Not equal to.
Equal.
Whether they are equal.
Yes.
Yeah.
There is nothing to suggest that we are testing for greater than or less than. So we test for difference. So in this case, we're going to say here, where is the guy? We're going to put here, not equal to. It's always important that you get that bit correctly because it guides the next step. So this is calling for a two-tailed test. It's calling for a two-tailed test. At what is the level of significance here? What's the level of significance here? This is the question.
5%.
Yes, very good. If it's not mentioned, the default one is 5%. By default, use 5%. By default, if you are not given an alpha, you use 5%. So this would be alpha over 2, which is 2.5%. And this will also be alpha over 2, which is 2.5%. And we all know when alpha is 5%, a two-tailed test, we always get plus minus 1.96. Okay, so once we are there, we move to the next step. Z-calc, x bar 1 minus x bar 2, divide by, we always divide by the standard error. Standard error, difference of means. And we have said that standard error, the difference of means, is given by, we're using S because we don't have sigma, we're using S. So this will be 3.4 squared over 125 plus 2.1 squared divided by 180. Someone simplify that for us.
$0.34.
Correct. 0. I want to have some modest.
34.
I want to have some modest
420.
etc. So keep that value in your calculator. So that will be, so our x bar 1 is 20.5. Is going to be 20.5 minus 19.0 divided by that answer. So we have 20.5 minus 19 divided by answer. Gives us 38 what? Around there, 4.386. Z calc. Z coefficient is there. Okay. So if the noise is coming from your side, mute yourself. So the next thing is to say whether this value is in the acceptance region or in the rejection region.
The rejection region.
Rejection.
Yes. So we can just come here and mark it. It is somewhere here. Not drawn to cell 386. So we observe that Z calc, which is 4.386, falls in the rejection region, critical region. Falls in the critical region. So what do we do? Hence,
Reject.
Yes.
we reject the null hypothesis. At the 5% level of significance. We reject the null hypothesis at the 5% level of significance. So what is our conclusion? Let's answer the question. I remind you what the question was. Test whether the two production lines are producing units with the same mean life of length. So let me paraphrase the question. Do you believe the production lines are producing units with the same mean life of length? Yes or no?
No.
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 Yes. So the two production lines are not producing units with the same mean life of length. The two production lines are not producing units with the same mean life of length. They are not equal. In other words, you can say the two samples are not coming from the same population. According to the evidence that we have, the two samples seem to be coming from different populations. They seem to be coming from different populations. So that was a nice question. Now let's see if there's another question. It was just that. Now so
Excuse me, Marim.
yes.
When we are coming up with a conclusion,
Yes.
is it always the case that okay, on a diagram, the part of acceptance, is it always the case that is we are looking whatever is within or outside there? The part of acceptance.
I didn't get your question.
Okay, I'm trying to mean when we are coming up with a conclusion, whether to reject or fail to reject, are we checking whether it the figure for Z-cal is is inside the acceptance or outside the acceptance?
Correct. That's why I put it here.
Oh, okay. Thank you.
I put it there to show that it is in the rejection region. It is in the shaded part. And that once it is false there, it tells you what to do with the null hypothesis. It tells you to reject the null hypothesis. Once you reject the null hypothesis, so this is what we have done. We have done that. So it means that according to the information we have, that is where the truth in quotes is. So mu1 is different from mu2. In other words, the two samples do not come from the same population. That's what it means.
Okay, thank you.
Yeah, that is basically it about two sample means. I'll give you some more questions for practice. I want us to move to proportions. So hypothesis testing.
This is how.
Before you move, Mwalimu.
Yes.
So if it was equal, if we could have failed to reject, that means it was from the same population.
Yes, it would mean that. It would mean that if
or probably if it was within the acceptance place.
Yeah, that's what we've just said. So if it was in the acceptance region, would fail to reject the null hypothesis. Okay.
And that means it's within the same population.
It means that, yes, it means that the two samples are coming from the same population. In other words, the mean, the population mean of the first sample and the population mean of the second sample are the same, are equal. That means it's just the same population.
Okay, thank you.
Yes.
Excuse me.
It's just like, just a minute. It's just like if I'm teaching this class, this is a part-time class, and I'm also teaching the weekend class or maybe the distance learning class. I give you a quiz and I give them the same quiz. My assumption is that you guys are entering this class with the same, what we call entry behavior. You are entering this class with the same entry behavior. You are all CPA-K, or you have done statistics 1 and maybe some other units there. So I'm assuming that you are the same kind of students. So I'll find the mean of this class and I'll find the mean of the other class. That is my X bar 1 and X bar 2. Then I may want to test the hypothesis that the two students, the two groups of students are equivalent. So that's my null hypothesis that mu1 is equal to mu2. So I may want, usually in my case, I may want to fail to reject the null hypothesis to show that whether it's a part-time student or weekend student, these students are just the same guys. They can even sit for the same exam. They can sit for the same exam, assuming that I've taught them the same way. And assuming that I've taught them the same way. So that's basically what we are doing here. That's basically what we are doing here. I think there was a question. I think there was a question. Yes.
Okay. So I'm just curious, how should we perceive a question that specifies that assume that the two sample size are dependent? That's one. And then number 2, assume that the two sample sizes, the two samples are independent.
Now, that's a good question. Huh? And we are relaxing that, that kind of assumption, okay? We are relaxing that assumption, and our assumption here is that the two samples are independent, because that only affects how you are independent, yes. So that only affects how you compute the standard error. That bit of independence or dependence only affects how you compute the standard error, nothing else. But in our case, we shall be assuming that we are working with independent samples. So we're assuming that the way the first sample was selected and the second one are completely independent, okay?
Okay.
Yeah.
Thank you.
All right. So, but we are very quiet about that kind of assumption. So our assumption will, in the background, we're assuming that we're assuming independence of the two samples. Now, let's move to hypothesis testing about one sample proportion. Huh? So the procedure will be the same. Maybe some of you will get bored because we'll be repeating what we've said. The only thing that will change here are the symbols that we use, because proportion does not use mu. Proportion here we shall be using pi, as we mentioned earlier. The sample proportion does not use X bar, it uses P. So we are just going to switch the symbols and we're going to adjust how we compute the standard error. We're going to adjust how we compute the standard error. But the formula for Z calculated remains the same after replacing the symbols, of course. So here, our null hypothesis will look like this, H naught. Our H naught will look like this, pi. So we're replacing mu with pi is equal to pi naught. So we test that against H1 that pi is bigger than pi naught, or H1 that pi is less than pi naught, or finally H1 that pi is different from pi naught. So again, as we said earlier, this will call for an upper tail test. This will call for a lower tail test. This will call for a two-tail test. So sorry, I should have shaded that. Huh? And this one will be a lower tail test like that. And this will be a two-tail test like that. So I'll not go to the details because we have already explained that bit. Then this is how you calculate your Z statistic, Z calculated. So Z calc will be given by P. So remember, we're working with these, X bar minus mu naught over standard error of that. So we're just going to switch the symbols. So this will be P, which is the sample proportion, minus pi naught, which is the hypothetical population proportion, divided by standard error of P. I know when we were discussing the confidence intervals, we defined how you compute the standard error of proportion. But here I'm going to make a slight adjustment in the context of hypothesis testing. We used P in this context, in the context of our confidence intervals, we were saying that standard error of P is equal to PQ over N. We use these estimates, P or Q, or P and Q, when the hypothetical population value is not known. When the hypothetical population value is not known. So if we happen to know the hypothetical population value, we use it. So here we say that standard error of P here is given by the square root. The formula is similar to this, but now we use pi naught. Then 1 minus pi naught, which is equivalent to P times Q divided by N. So when you're testing hypothesis, we always know pi naught. So we use it. We don't use P when you already know pi naught. So that's the story. Okay. So the other stories are easy to see. N is the sample size. Pi naught is the proportion of is the hypothetical population proportion, so on and so forth. So let's go to the example because the other steps are the same. Example, and we'll pick the example from your notes. One proportion. So we have this question here. We have this question here. A manufacturer of computers claims that his computers are operational for more than 80% of the time. Percentage of time. Huh? During the course of 1 year, one computer was operational for 270 days. Test at the 1% level of significance whether the manufacturer's claim was justified. So for instance, if this manufacturer was coming up with an advert, maybe a TV advert or a radio advert, and they want to make this claim in the advert, you decide to test it because you have done some statistics. Will this claim be justified? Will this manufacturer be telling the consumers the truth, or the guy will be exaggerating or lying? Okay. So that's what you want to test here. But let's see, what are we given in this question? We have 80% here. What is that?
P. Hypothetical.
P naught.
It is pi naught. It is the population proportion. So that's our pi naught, 80%. We prefer to have it as a decimal like that. The claim about all his computers is that. But now you decide, maybe you have bought this computer from this place and you observe this computer for a whole year. You observe this computer for a whole year and then it's working for 270 days within a year. So what are we getting there? What is 270? What is 270 days here?
P.
Remember
Population.
what we said last week. Huh? P is a number between, and how do we define P? The number of success outcomes divided by n. So P is always a number between 0 and 1, just like 0.8. Huh? So what is this 270? No.
1.
Yeah. 270 is the number of success outcomes out of 1 year. 1 year has, so our n will be the number of days in a year. We shall assume it is 365. So our P will be 270 over 365. The proportion of time that the computer was working properly. That is what you will check. That is what you will use to test the hypothesis that the computer is working on 80% of the times. Hope we are there. So let me transfer the stories here. So we have pi naught, 0.8. We have P is 270 over 365. Let's have that value rounded to
0.739.
So let us round it off to 0.74 for simplicity. Yeah? Okay. So let's round it off to that value. Then we have our n, 365 days. And I think we are set. We are good to go. We are good to go. So the starting point is null hypothesis. Pi is equal to pi naught. Pi naught. So if the noise is coming from your side, mute yourself. If you know the person, you tell me to mute him. I can't know who is making the noise unless I check, unless I stop sharing the screen. Then H1, we get that from the wording of the problem. What is the question suggesting, or what are we trying to test here? Let me take you back to the question. This guy here claims that his computers are operational for more than 80% of the time. That is the claim that we are testing.
Okay.
So what is the suggested alternative hypothesis?
That pi is greater than.
Greater than. So we're going to have pi is greater than 0.8. That tells you that we're going to have an upper tail test. That tells you you're going to have an upper tail test. 0 there. An upper tail test. And this is, we're going to use 5%, I think so. So this is alpha is 5%. So this is Z critical. Z critical is there. We said this is what value? I've not crammed these values. 1.65, is it so? Is it so?
It is.
Oh, good, thank you. So once you set up your critical region, the next thing is to obtain your Z calc. You use P minus pi naught divided by standard error of P. You can start with the standard error of P, which is the square root of pi naught, 1 minus pi naught over n, which is equal to 0.8 times 0.2 divided by 365, everything under square root. Everything under square root.
.021.
Yeah, if we round off, we get
0.021.
Yeah, all right, that's okay. Then I come back to my Z calculated, P 0.74 minus 0.8 over that value. So I prefer to round off the last thing. Rounding off is my last thing. 0.74 minus 0.8 divided by answer. Gives us
Negative 2 points.
8657.
Something like that.
-2.857.
Minus 2.8 something. Huh?
857. 857.
Yeah. Then let's. Where does this value fall?
Acceptance.
Acceptance
region.
It falls here. It's deep in the acceptance region, actually. It is deep in the acceptance region. So Z calc, which is a minus 2.866 or around there, falls acceptance region. So that tells you what to do with the null hypothesis. Hence, we do what? Collister, is it?
Fail to reject.
Yes.
We fail to reject.
Fail to reject. We never accept. We never accept. We fail to reject the null hypothesis. At the 5%.
At 1%.
Yeah.
It was at 1%.
Who said so?
We are at 5%.
The question, test at 1% level.
But at what level did we use in our question?
We used 5%.
We used 5. Yeah, so we have used 5%, not 1%. You can do 1% at home. Huh? I did notice that we were given alpha is 1%. So we have used 5%. All right, yeah. So you can see how the question will change if you use 1% at home. Huh? So at 5% level of significance. So what is our conclusion now? In your conclusion, you must answer the question that was presented to you. The question was, test whether the manufacturer's claim was justified. So is the guy justified?
Yes. Yes.
So let me take you back to the hypothesis. So what have we done? This is what we have done, isn't it? We have done that, isn't it?
Yes.
So when I tick the first one, the other one is a cross. So is the manufacturer's claim justified? I'm repeating the question.
No.
No.
This was the claim.
Oh.
That was the claim. The guy was claiming that the computers are operational for more than 80% of the time.
No.
No.
No. No.
Yeah. So the manufacturer's claim is not justified.
Since it was greater.
Is not justified. At least according to the data that we have. According to the data that we have, the manufacturer's claim is not justified. It's not justified. So that's the answer to the question. The answer should be in simple language, in a layman's language, not in a statistical or technical language. Okay, so that is it. I guess we have some other example. So please repeat that example using 1%. And for your practice, you can even use 10%. I think we have not used 10% anywhere. You can also use 10% and check how the decision changes, so on and so forth. All right, so there's some homework here. There's some homework here. the proportion of drivers who plead guilty to driving offenses is usually 60%. I don't know in which country. So out of 750 prosecutions, 400 pleaded guilty. So clearly, this is your pi naught. And out of, so this is N is 750, and 400 is the number of success outcomes. So P will be 400 divided by what? 750.
750.
So you need to define the correct hypothesis here. You can solve this and then you let me know through the WhatsApp group. You can even share with your friends. I don't have to know, by the way. You can just get the answer and try to share with your friends. Then you see if you're going to get the same thing. If maybe there are some disagreements, I can come in. No? I don't think I need to come in here. These are very simple questions. So you can try that at home, so that we, in the remaining 1 or 2 minutes, we look at hypothesis testing about two proportions. I'm sure I'll be repeating myself, so I know some of you will get bored because we are repeating the same things now. What is happening? So hypothesis testing about two proportions. So the procedure is similar to the one we saw in the case of two sample means. We only switch the notation and adjust how we are going to compute the standard error. So in this case, we have H naught, that pi 1 is equal to pi 2. We test that against H1, that pi 1 is less than pi 2, or H1 such that pi 1 is greater than pi 2, or H1 is such that pi 1 is different from pi 2. So similar to what we did in the case of means. Okay, so the first one is calling for a lower tail test. The second one is calling for an upper tail test. And the last one is calling for a two tail test. Then Z calculated, Z calc will be given by P1 minus P2 divided by standard error, difference of proportions. Standard error for difference of proportions, where the standard error P1 minus P2 here will be given by P hat times Q hat, 1 over N1, 1 over N2. I think we mentioned this last time. Then you take square root. Okay, then P hat is N1 P1 plus N2 P2. N1 plus N2. We mentioned this last week. Then Q hat is 1 minus P hat. Again, we're assuming independence, like that. So that's basically it. That's basically it. So it's very good for you to notice how we are computing the standard error in each of the cases. Standard error in each of the cases. In those 4 scenarios, 1 sample mean, 2 sample means, 1 sample proportion, 2 sample proportions. It's good that you note how we are obtaining the sample standard error in each of the cases. So once you know that, the story will be quite simple. Example. Let's pick the information from our notes. Example 1. This is an example in marketing. I'm very surprised there are no marketers in this class. Anyway, so a market research organization carried out a sample survey on the ownership of washing machines and concluded that 64% of all the households owned a washing machine out of a sample of 200 households. So 6 months later, they repeated the survey using the same questionnaire and concluded that 69% owned a washing machine out of a sample of 150 households. And here's the question. Is the difference due to a significant increase in the ownership of these machines, or is it a mere random sampling error? Beatrice, your hand is up. Please go on. Beatrice Jugona. Beatrice Jugona. Beatrice, do you have something to say so that we move on? Huh? Beatrice, I've asked you to unmute yourself.
Takes more of a spiritual angle, but I know it covers many things. But
Beatrice Jugona, I think maybe your hand went up by mistake. Huh? So let's not what we are given here. We are given 64%. This is a percentage which is coming from a sample. So this is our P1, 64. And corresponding to that is our sample, is our size of the first sample, 200. And then we have another proportion here, 69%, which is our P2, 0.69. And that proportion is coming from a sample of size 150. Basically, that's what we have. So let me transfer that story to the other side. So here we have P1, 0.64. N1 is 200. We also have P2 is 0.69 and N is 150. The question is, test whether the difference is due to a significant increase in the ownership of the washing machines, or is just because we used a different sample. That's what we're calling a random sampling error. Is it just because we used a different sample? Like you saw when we were testing, when we were doing the sampling distribution for X bar, we were getting different samples. We were getting different samples every time sample means every time we pick a sample, though they are all coming from the same population. So that's what we want to test here. Let's define our H naught. And just like we saw in the case of two sample means, we never use any specific value. So we have H naught that pi1 is equal to pi2. That will always look like that for all the hypotheses, for all the problems. Then H1 will be guided by the problem. What are we testing? We're trying to check whether the ownership is increasing, the proportion of ownership is increasing. So we shall have pi1 or pi2 there. How do we test whether there is an increase? Do we use less than, or clearly we don't use a not equal sign. No? We want to check whether the percentage of ownership is increasing. It looks like it is increasing from 64% to 69%. We want to test whether that is a significant increase. So which symbol do we use here? A less than or a greater than?
Less than.
Greater than.
We use a less than sign. We want to check whether pi2 is bigger than pi1. We want to check whether the second proportion is bigger than the first one, or whether the first one is less than the second one. So we use the less than sign there. Very critical there, okay? So that is calling for a lower tail test. So once you do that correctly, the other things just fall into place. Lower tail test. We given alpha, or we can use 5%. Let's use 5%. So this is minus 1.65. That's our Z critical. So from there, let's get our Z calculated. Z calc. P1 minus P2 over standard error, difference of proportions. So standard error, difference of proportions. We said that the formula is quite interesting. 1 over N1, 1 over N2 square root. So where P hat is N1, P1 plus N2, P2 over N1 plus N2, where N1 in this case is 200, P1 is 0.64 plus 150 times 0.69 divided by 200 plus 150. So that's how you get the P1. I mean P hat. Huh? Anyone who has done it quickly? Are you getting something? 0.66, huh? 0.66. Huh? So that tells us that Q hat is 1 minus 0.66. Huh? So let's round off to 0.66. Huh? So this gives us 0.34 as our Q hat. So our standard error, difference of proportions, will be 0.66 times 0.34 multiplied by 1 over 200. This is 1 over 150. Then I take square root. Take square root of that. If you do your math well, 0.051 etc. It looks like that. That's the standard error. Then from there we can get the Z calc. I want us to stop in the next 5 minutes. Huh? So let's get our Z calc. Our Z calculated will be P1 0.64 minus 0.69 divided by 0.0511. Minus
0.9785.
I want to round it off to 2 decimal places, huh? Because usually, yeah, so we have
8.
So I need to make a decision. Where does it fall?
It falls on the unshaded region.
It is called the acceptance region, minus 0.98, somewhere there. So I need to say what I need to do with the null hypothesis. So we're saying that Z calc, which is minus 0.98, falls in the acceptance region. That means we do what?
Accept.
No.
We
fail to reject. We fail to reject the null hypothesis at the 5% level of significance. So that is where the statistics end. We want to make a conclusion in very simple language. Conclusion. You go back to the question and try to answer that question based on the information that you have so far. So the question was, is the difference due to a significant increase, or is it a mere random sampling error? Is there a significant increase in the ownership of these machines, or is just simply because we sampled another time? Huh? We used a different sample.
It's because there's a significant.
Because we used another sample.
So what is the conclusion? Is there an increase or there is not?
There is.
There is not.
No increase.
So what have we done? Let me mark out what we have done. We have done this. We have done that. I've put a tick somewhere and I've put an X the other part. So do you, according to what I've put there, is there an increase or there is no increase?
There is an
There is
increase.
not.
There is an increase.
There is no increase. Pi 1 is equal to pi 2.
Yes.
There is
There
no
is no
increase. There is no increase.
And
So
we rejected the hypothesis.
whatever looks like an increase from 64 to 69% is a mere sample error. It's just simply because we used a different sample, but the
Yes.
two values are significantly not different. Okay. So let's answer that question. Increase in the percentage of households that own the washing machines. There is no significant increase. There is no significant increase in the percentage or in the proportion of households that own the washing machines. So any apparent increase is just a mere sampling error. It's just a mere sampling error. There's nothing. There's nothing. So guys, I want us to stop there. It is good for you to note that we were testing hypothesis when we are assuming that we have a large sample, that is n is large, and when the sample is random. When n is large and when it is random. That's why even in the context of proportion, we know proportions come from the binomial distribution. We know proportions are not coming from normal distributions. We are able to assume normal distribution based on what we said on about the central limit theorem. If you recall the second statement of the central limit theorem, we can always assume normality of the sample statistic if we pick a large sample. So in this context, we were picking large samples and they were all random. That's why we're using Z. Now, the next thing I want us to do, and I'll just slightly touch it, is if we violate the assumption of a large sample, if we pick a small sample, then what happens? We switch from the Z to another distribution called the T distribution. And the workings will be the same. It will be so repetitive. I may not want to cover it, but I just mentioned something about it. But we shall just be repeating what you have done, but using a T, not a Z table. Any questions? Are there any questions as far as today is concerned? Yes. I'm sorry, I've used a lot of your time. I'm sorry about that. We should have stopped a long time ago.